Hello and welcome to Data Science in Industry vlog. Today I would like to start a discussion about the integration of our AI algorithms with the control system of a factory or of a plant. So the control system is the brain of a plant. It is really crucial to understand the operation of the algorithm that creates the control system, because we have to augment this brain, extend this brain with our intelligent algorithms. So in the series of videos, I would like to discuss the IT tools that are used to develop the control system. I will discuss the distributed control system. I will discuss some theory related with the control strategies. I will tell you what is the closed loop, the PID controller, what is the feed-forward control and the cascade control. So this is very crucial to understand the operation of the control system. So all those ideas, all those topics that I have mentioned, I will not go deep into those topics. I will rather try to explain you some basics, so you get a feeling of the control system, of the basic strategies, and it will help you to connect your AI algorithm with the control system. So decisions made by the AI algorithm will be able to send directly to the control layer of a plant or the factory. I hope that you will understand how to read the values from the control system, current values and the historical values, how to send the decisions back to the control system, how to create basic operator graphics, how to connect the AI algorithm with the control system in a safety way, in a way that the AI algorithm is aware of the fact if the plant or the factory is ready to start cooperation with the AI algorithm, and in the reverse way, if the control system must know that the AI algorithm is ready to operate and ready to send decisions to the control system. Moreover, I will explain you how to create a nice connection between the AI algorithm and the operator, the dispatcher, so the dispatcher has a full control over our algorithm. He can decide which devices can be controlled by our AI algorithm, how to switch it off, how to switch it on, such things. And moreover, I will explain you how to make modifications of the basic control algorithms, so they are ready to get the decision. They are ready to include the decision of the AI algorithm in their control strategy. So how to pass this decision to the control layer in a safety way, of course. This is safety first, always. I think that most of those topics that I have mentioned I will cover in the third or fourth video, because at the beginning I have to start with the basics. So today I will talk about the distributed control system and PLC controllers. You will understand what is the distributed control system. And in the next video, you will understand what is the PID controller, closed loop, etc., etc. And then in the next video, in the last video, we will discuss all the details of connecting the AI algorithm with the control layer. So why we are talking about this, why we are talking about the control system? like I say, it is the brain of a plant or a factory. So let's say devices like fans, pumps, valves, those are the actuators, those like hands and legs, right? But the control system is the brain that synchronize the operation of all those devices. Usually if we are dealing with the AI algorithm, we have to cover the complex system. We have to make them predictive models of a complex system. We have to optimize the complex system. We have to predict failures in the complex system. So this complex system usually consists of several devices, of many devices that are connected, that together they are constituting the industrial process, the big part of the industrial process that we have to cover with our AI algorithm. So it's not enough to understand the operation of a single devices. We can download the characteristic of a pump, we can understand it, we can check the characteristic of a fan. Okay, we have to do this. But it is crucial to understand how those devices are cooperating together, how they are synchronized in order to achieve process goals, to achieve proper temperatures, pressures, flows, etc., etc. And this is the task of the control system, right? So before we try to create, before we develop a predictive model, before we develop the optimization strategy or the algorithm that checks for anomalies or predicting failures, we have to really understand the basic decision layer, the basic control layer that decides about the operation of a particular devices. From the AI algorithm point of view, those devices, but also the control system that synchronize the operation of those devices is a complex system that we have to cover. And the control system is a crucial part of this control system. So you can imagine that our inner control system controls how we walk, right? Our inner basic control system takes care that first we will move the left leg and then we will move the right leg. Left leg, right leg, left leg, right leg. We don't have to think about this. It is covered by our basic control layer. Our, let's say, higher intelligence can plan that we will use those legs to go to the shop and buy some bread and milk, then go to the office, then maybe take kids to the swimming pool, right? So we don't have to utilize we don't have to worry about the fact how we will use our legs in this process, right? We are focused on our decisions, what we will do today. But of course, in such planning, we need to utilize constraints related with the basic control system. We need to be aware that we cannot walk with the speed of light, right? Usually it's like 4 or 5 kilometers per hour. So if we have to go to the office and be there at 9, let's say, and we need to be aware that if you would like to walk, of course, we need to be aware that it will take us half an hour. So we'll have to leave our home at 8:30. Maybe we would like to run. It's also possible. But then we will have to be aware that after a while we could be tired and our speed will essentially drop. So In the same way, we have to be aware of the control system of a plant or of the factory. If we will decide to change the set point for a temperature, change the load of the device, we need to be aware what are the constraints related with the control system, how it will be done, how it will affect other part of the process, right? If we, for instance, if we have a power boiler in the power plant, we need to push the air to the combustion chamber, because in the combustion process we need the oxygen, so we need to push the air. It is done by forced draft fans. If we would like to increase the load of these forced draft fans, we need to be aware that the control system will immediately send a signal to the induced draft fans, other fans that take out the exhaust gases from the combustion chamber. So the control system will send a signal to increase the load of these induced draft fans. And if we will overload those induced draft fans, they will hit 100% load, other part of the control system will immediately change the set point for produced megawatts. There will be a drop of megawatt, our main production goal. So in the power plants we produced electrical energy, we produced megawatts, so we do not want to decrease the amount of our production, but for the safety reasons the control system will do it. So we need to include all those facts in our decision strategy related with those forced draft fans, those fans that push the air into the combustion chamber. This is just one of the examples, but I hope that you understand this need. The AI methods are not, a magic box where you present some input data, some output data, you will get some model, and then you can implement it in reality. With such an approach, without taking into consideration the decisions, the strategy of making decisions of a control system, our algorithm can be very dangerous to the factory or to the plant. Nobody will trust it. There will be a failure sooner or later if we'll do this. Okay, so now, like I said, I will start with the distributed control system. I will describe what it is. Generally, it's a IT network full of interesting devices that help us to control the plant, to supervise the plant, to see how the plant is operating. And this is our gate to the plant, to devices, to processes. We observe the process through the distributed control system. We change the control strategy through a control system. We read the sensor values from the distributed control system, and we send our recommendations, our new decisions to the distributed control system. So it is really important to understand what it is. In the first slide, I would like to briefly present the idea of the distributed control system. So it's the IT network where we will find such devices as controllers. Here in this picture we can see only one pair of controllers. Usually we have many cabinets, where in each cabinet we'll have a pair of controllers and also the input-output modules. We will also find a lot of sensors connected to those I/O modules that measures pressures, temperatures, flow, liquid levels, etc., etc. On the other hand, we also have actuators that affects our process, like valves, pumps, engines, etc. And they are also connected to input-output modules. The decisions calculated in those controllers are based on the sensor values, are sent to the actuators, right? So if the pressure is too low, we will close the valve. If the pressure is too high, the controller, the algorithm that operates in the controller memory will calculate that we should open the valve. Okay, and we also have the network that sends the information from sensors and the values of other variables to other controllers. The controller number, 10, can utilize the information from I/O module that is connected to the temperature sensor, for instance, that is that sits in the cabinet 3, where the controller number 3 is located. So because of this network, because of the highway, the information about the values is spread to other parts of the distributed control system. Yeah, the distributed, right? This is the important word here, distributed. It is distributed because we don't have one master server, one master controller that controls the whole plant. We have a set of controllers, and each controller controls part of the process. Okay, moreover, we have operator stations. Operators can observe the process, can check what are the values of pressures, temperatures, etc., etc. They can observe trends. They can observe alarms. If the temperature is too high, the operator will see the alarm on the alarm list, and he will have to react this way or another. So, using the operator stations, operator can also react. They can change the load of particular devices in a manual mode, so they can, let's take this example with the pressure, right? If the pressure is too high, we would like to open the valve. It is normally done by the control system in automatic mode. But if for some reasons the pressure is still too high, or the operator is not happy with this pressure, he can switch to manual mode and he can change the load of this, change the opening level of this valve manually. Well, not manually, so he don't have to go there and do this by his hands. He used this DCS system, distributed control system, and in the distributed control system he changes the mode of the control station related with this device, with this valve, from automatic mode to manual mode. Right? He also can increase the set point for add some bias to this set point for pressure, right? So if he's not happy with the pressure, if it's still too high, he can also lower the set point for this pressure and stay with the automatic mode, hoping that the control system will do its job. We also have engineering stations where we can change those algorithms, those control algorithms. If we are not happy how the pressure is controlled by the valve, we can change something in this algorithm, make it more aggressive, maybe, add some external information that can be used to improve the operation of this algorithm. We can also change the operator graphics, add new devices, register new devices, create new alarms, right? So if this pressure will be higher than some level, the new alarm will be raised and present to the operator. We also have a historical data server where the historical values of our sensors are stored. Not only sensors, some artificial variables can also be stored here. Like, for example, the status of the AI algorithm seen from the distributed control system perspective. This is not a sensor value, but it's a variable, a process point, or a tag, depending what kind of DCS we are using. There are different names for it, but it also can be stored in the historical data server. And such information can also be utilized by controllers. So, generally speaking, if we will integrate our AI algorithm with a distributed control system, we will have to make some modifications in the algorithms that operate within controllers, so they are able to use our decisions and send control signal to actuators. Moreover, we need to do some modifications here in the controllers, in the algorithms, to allow the safety connection. Right? So to check if the AI algorithm is alive, to develop some layer of communication with the operator, so the operator can somehow decides when to run the algorithm, when to stop it, and of course the operator will not dive deep into those algorithms. He have his own operator station here, so we'll have to do some modifications to operator graphics, make a new graphical user interface, a new window that helps the operator to communicate with our AI algorithm, to present our decisions, recommendations, how to use the plant, is there a risk of a failure, such things. All right, and of course, we will also like to read the points, so we will read them from this highway, from this network, the live data. We can also read the historical data from the historical data server if we are planning to do some identification experiments to increase the variance of the data, to check how the process responds to decision changes. We'll have to add important variables related to our task to this historical data server, and then download it to create characteristics, create predictive models. Yeah, basically those are the main components, and of course the next videos will dive deeper into particular components of the DCS, of the distributed control system. But first, I would like to start with PLC, with Programmable Logic Controller. So this is a very simple PLC controller. It has some inputs. Those X pins, those are the X pins here, those are the inputs. It has also some outputs, those Y pins. So it's a microprocessor device used for automation of technical processes. So we can connect a sensor, let's say the flow sensor, to this PLC controller, or let's say the sensor from the that checks the level, if the level of the liquid in a tank has been reached, right? So if it's not reached, it's 0. If it's reached, it's 1. Such simple sensor. And then we can implement in the algorithm within the memory of this device. And this algorithm will be running in a loop, will be executed every second or 10 times a second, or other time or other frequencies. Well, we can specify the frequency, and if it's the sensor that checks if the level of the liquid have been reached in a tank, we can say that, for example, the algorithm will check when the value of x1, if we will connect the cable from the sensor to x1, has a value of 1. If it has a value of 1, it will, I don't know, stop the pump, right? So the cable to the pump is connected to the, I don't know, Y0 pin, and the algorithm will send the decision to Y0 pin to stop the pump. A very simple algorithm. And it will be executed in a loop every second, every 10 times in a second, or other frequencies. So first we'll have the auto diagnostics. If everything is all right with those cables, with those values, with the memory, with the PLC. Then we will read the values from inputs, execute the program, also send the values to other controllers, because usually we have more than one PLC controller in the factory. So usually it's about factories, not a plant, but it also can be implemented in a plant. But let's assume we have many of such PLC controllers. So we will maybe other controllers, other algorithms that sits in the memory of other controllers would like to know if the level of the liquid has been reached, right? So they need this information. And on the end of the loop, we will write the output data, so we'll send the decisions to, for instance, to the pump, to actuators. PLC controllers are rather dedicated for smaller plants, for factories where we have mostly discrete production. In such like automotive industry, in such places you will find usually PLC controllers. Or in case of continuous processes, it's rather dedicated for smaller processes, like, for example, I don't know, heat substations in the buildings. We can, for instance, in case of a factory, we can, for instance, use the PLC controller to control such a simple process where we have, I don't know, apples that are entering boxes, and we have to pack apples into the boxes. So our algorithm will start the apple conveyor if there is a box. So here's the box sensor. If we will count to, I don't know, 10, we will stop the apple conveyor and start the box conveyor, and wait till the empty box reaches the box sensors. Then we will stop the box conveyor, start the apple conveyor. The box will come to the box. The apples will come to the box, and we'll repeat it for infinite, until someone will press the stop button. So this is a very simple case, perfect for the PLC. We can create such an algorithm using the ladder diagram. I will not go down into what is the ladder diagram. It's the way how we can program the PLC controller. If you like to understand how the ladder diagram works, write in the comment. I will make the video about this. If we will open the PLC controller, we will find CPU, we will find memory blocks where the algorithm is located. We'll find communication modules, some Ethernet cards that allows the communication between PLC controllers if we have more than one, and usually we have more than one. And what differs such a PLC controller than the standard PC is that we have a lot of external pins, inputs and outputs, where we can plug the cables from our sensors to our actuators. We can have different types of these pins, digital and analog, inputs and outputs. So the difference is like between the VGA and HDMI cables, right? So if we are sending the signal using a string of zeros and ones, high and low voltage, or the continuous range of voltage or current is the carrier of our information in case of analog signals. We can have also binary two-state inputs and continuous inputs and outputs. Those binary inputs are, for example, the engine is started or stopped, valve is opened or closed, water level is reached or not, right? Binary inputs are what is the level of valve opening, what is the load of the engine, right? What is the level of the liquid. In case of outputs, the same. We can have binary outputs, start, stop the engine, open or close the valve, or continuous outputs, like for example, so something like floats, let's say, like for example, set the load of this engine to 69.1%, open the valve to 20.5%, right? And of course, this word analog is sometimes well, maybe I will put it this way. You always have to check what does it mean. Because sometimes people refer to analog input or output as the float. So it's not the way how the information is sent using the string of zeros or ones, or I don't know, using the current or voltage. So it's not the information if it's the VGA or HDMI cable, but it's the information, or is it the binary two-state value or continuous value. So every time, please take the manual to this particular PLC or talk to the automation guy in the plant or in the factory to know what you're talking about with your customer, with your business partner. Okay, there are many ways of programming the PLCs. We can have ladder diagrams like this. This is one of the oldest way of programming the PLCs from the historical point of view, and very popular. We can have something like functional blocks. Here you can see, for instance, the definition of the algorithm that controls the water level in a drum in a power plant. So it consists of, for example, two PID controllers in a cascade, So the one PID controller sends the information and calculates what should be the set point for a low level, the secondary PID controller. In this particular case, what should be the feed water flow, the set point for feed water flow. There are maybe some gains, some limits, some denoising blocks that we can use. So once again, if you don't know how to program particular PLC, take the manual, talk to the automation guy. I'm talking to you about this because every time you are doing the project, at least we are doing this, every time we are starting the new project in a factory or in a plant, we are asking for exports of those algorithms from the PLC controllers or from the DCS system. We are asking for exports of the control algorithms to understand the operation of the particular factory of the plant, or at least the part of the process that we should cover by our algorithm. Sometimes it's the export, sometimes we are sitting with our customer, with our business partner or scientific partner in the plant, in the factory, and watching those, analyzing those algorithms. So we need to know how to do this. Okay. If we have those controllers, it's good to also have the system that allows us to observe the process and to also to allow us to decide about particular aspect of the process. And this is the SCADA system, the Supervisory Control and Data Acquisition System. It's dedicated for supervision of technological process. It is responsible for current data acquisition. So we have a database, and the current data are stored in this database. Then they are visualized on the operator graphics, so the operator can see what is the flow, what are the temperatures, on top of some graphics that represents particular devices. He can observe trends. He can also observe alarm lists. So if there's too high pressure, he will see that he need to react and do something, like opening the valve, for instance, if it's not done automatically by the control system. The process controls, so the operator must have some tools to control the process, right? If he's not happy with this pressure, he can switch to manual mode for a valve and inform the PLC controller what should be the value of the valve opening. So he put this value in a SCADA system, the operator. It should be, 30%. And then if the thread is over, he can switch back to automatic mode, for instance. The SCADA system also allows for historical data archiving. So all the interesting historical data that can be used to train the AI algorithm are in the SCADA system. We can export them and use them for training purposes. Use them for updating the characteristics of a process, updating our predictive models. And the SCADA system is superior to PLC controllers. So PLC controllers are connected to devices, right? To actuators and sensors. So they are sending decisions to actuators. They are reading sensor values and process them, right? they are performing the control algorithms. But from the SCADA system, we can send our decisions to controllers. We can see the values of sensor, the sensor values. We can store the historical data. If we have PLC controllers from different vendors, like few PLC controllers from this particular vendor, other part of the process is covered by PLC controllers from other vendor, the SCADA system is from the third vendor, then we need to somehow integrate all those islands together. We can use, for instance, the OPC server to connect the SCADA system with the PLCs, or use some industrial protocols that are usually handled by PLC controllers and the SCADA systems. If everything is provided by one vendor, usually there are dedicated drivers, so the connection is easier. If we want to connect to the SCADA system because we would like to read the data and send our decisions to the control system, we can also use, for instance, the OPC server or a dedicated driver. This is example of the SCADA system. Sorry, it's in Polish, but here you can see, for instance, temperatures of the steam, the flow of the steam, some trends. Here's the trend of the water level in a drum. So yeah, this is how it looks like. Okay, and now let's go back to the DCS system. So the distributed control system is responsible for control and visualization of technical processes. In comparison to this PLC SCADA approach, we can say that it has a common database for control and for visualization. So if you have a sensor, let's say the flow sensor, and we'll associate the name of the variable, associated the variable with the sensor, let's call it, U4 PF003. Right? This is the name of the variable that represents the flow. It will have the same name in the control algorithm, in the visualizations, in the operator graphics, in the historical data server. So it helps to manage such a process, such a large scale process. Sometimes it's up to several hundreds or even millions process points or tags, process variables, depending how you will call it. So it's a huge number, and every second you have to process them. You have to read them, do something with them, calculate new control signals and send them to actuators every second, or 10 times a second, or even sometimes with a higher frequency. So the functionality of a DCS is very similar to the functionality of a PLC and a SCADA system. But of course it has this common process point database, and it has a high reliability. It's a very robust system. So this is a system dedicated for online control of continuous process, rather continuous, right? The heavy industry. Those are large-scale processes where we cannot just easily stop them, right? With automotive industry or generally discrete processes, the operator observes the alarm list, and if something happens, there is a red button. He can stop the line, fix something that should be fixed, and start it back. in case of heavy industry, you really have to play with the process all the time. You have to tune it here, tune it there, reduce some threads here and there. Maybe the temperature are too high somewhere, so you have to act. You have to reduce the set point for this temperature, or open some kind of cooling water valves. Maybe the pressures are too low, so you need to close the valve somewhere. So it's you have to dance with the process using the DCS. It's hard to just stop the process because it costs a lot and it takes time. So we rather avoid stopping the process in case of heavy industry. So the DCS systems are characterized by very high reliability of the whole system and its individual elements. And they are distributed, right? So we don't have one master computer that controls the whole world, the whole process. We have a set of controllers, and it also increases the reliability. We have the automatic maintenance of control functions even in case of breakdowns or disconnection of some components, like controllers. The programming of control function is usually easy and flexible. Moreover, we don't need to stop the plant to create and load a new algorithm or modify the existing ones. It can be done in online mode without any harm to the process. However, some plants have a strategy to not to change the control algorithms while the process is while the factory or even the plant is working. So first you have to stop the process, industrial process, and then you can modify algorithms for the safety reasons. Many elements of a DCS system is redundant. So if we have those controllers, usually it's a pair of controllers that they are twins. If there is a failure associated with one of the controller, another one will take the responsibility for controlling the plant or part of the process, right, associated with this controller. Crucial sensors are redundant, right? Like crucial process parameters are measured using, let's say, 3 sensors. If one of them is out of service, still we can rely on 2 others. And we can efficiently handle very large plants. Hundreds of thousands, millions of process points. So a DCS system is responsible for acquiring process data, for process control, like typical control tasks like maintaining the temperature on desired level or pressure flow, but also some protection algorithms, what to do automatically if something goes wrong. How to decrease the load of the device or even shut down the whole unit in a safety way, of course. The alarming, right? So how to inform the operator that there is a threat that should be addressed. There is an IT network that allows for information flow to all components of a DCS system. We have those operator stations that allows for visualization, alarming, and operator tools for process control. I will talk about them later. Of course, data archiving, very important thing for us if you would like to train our AI algorithms based on the historical data. And engineering functions that allows for diagnostic of the whole system in online mode, that allows for modification or creation of a new control algorithm and loading them to the memory of a controller the functions that help us to create new or modify existing operator graphics and load them to the operator stations. And of course, if you are implementing the AI algorithms, we will use this engineering station and the engineering functions to register new variables in the system, our decisions, right, or our algorithms decisions, to modify control algorithms so they are able to handle our decisions, and modify operator graphics so the operator can have a control over the operation of the AI method. Here you can see the components of a DCS system. So we have those cabinets. In each cabinet you will find controllers and IO input-output modules. The sensors and actuators are connected to those IO modules. There is a network that connects all the controllers and all the operator stations, engineering stations, sometimes other computer in the plant network uses the information from this from the DCS. I don't know, automatic billing system, right, or other systems. And of course, our computer that or our server, right, that where the AI method is installed should also be connected to this network. So we are able to send the decisions to controllers, or at least read the decisions, read the sensor values, and send recommendations to operator stations for dedicated new graphical user interface, where the operator sees that there is a risk of a failure, or what should I do with the device. So we need to plug such a machine, such a computer, to the network. And we should do it in a safety way. All right, so now I will discuss briefly all those components. So I will start from IO modules, the input-output modules here. So we plug the cables from our sensors and from our actuators to those input-output modules. They are responsible for reading the data from those measurements, from those sensors. In the input-output module, we can transform the current signal into digital form, and in the reverse way, we can also transform the digital information into the current or voltage signal that will be passed to the actuator. We have four types of those inputs and outputs. Binary inputs, I already discussed them. Continuous inputs, sometimes called the analog inputs. I don't like this name. I already explained why. So thermocouples, pressure measurements, valve opening levels, etc. Binary outputs: close the valve, activate the feeder, stop the engine, right? And analogs, or I rather would like to say continuous outputs, like set the valve to 65.8% opening. There is some automated diagnostics already in our module. So if we will check that, if the IO module will check that we cannot trust the sensor, for instance, right? Because we have we read 0 milliamperes, and we should read something between 4 and 20 milliamperes. Then it will associate a bad quality with this value. So in the DCS system, you don't only have values, but you also have the qualities of this value. It can be good, the quality can be good, can be bad, can be poor. There are different levels of this quality. But if the quality of the sensor, if the quality of the value is bad, it will automatically be utilized in the algorithms, in the control algorithms, because we cannot trust such a value. And for instance, some control loops will be automatically switched to manual mode, and the operator will have to decides about the load of devices manually, because the control system cannot trust this information. What is the sampling time? Usually it's 1 second or 100 milliseconds, but sometimes for critical measurements it's 10 milliseconds. Usually the higher frequencies are not possible. If you would like to measure vibrations, I don't know, on the turbine or something like this, you will have to have a dedicated system for this. So here is the here you can see two controllers and I/O modules. You can unplug the I/O module and then plug it again. Generally, it looks like this. So if you plug the cable to the pin, you need to register it in the system. So you need to say that the I/O module number, I don't know, 26, the pin number, I don't know, 17 this is the temperature of the steam, right? And we should associate the name with this. We can set some alarms, etc., etc. Okay, so now the crucial element, crucial component, controllers. The controllers are responsible for base control. So here we are implementing the control loops that usually utilize the PID controllers and other control structures. I will talk about them in the next video. Using these loops, we can control, temperatures, flows, pressures, load, etc. But also we can implement sequence control in such a controller. So we can implement startup sequence of particular devices or the whole units. For this purpose, we can use the ladder diagram, or we can use other dedicated algorithms and programming functions. Okay. We can, in some DCSs, we can even use some advanced controllers, some advanced algorithms that, for instance, are responsible for advanced control of the multi-input, multi-output process. Rather simple one, but still there is such an opportunity. If we will check the hardware and software, so this is how it looks, such a controller, right? So there's always a twin, the main one and the secondary one. If the main one has a failure, the secondary one will automatically take the responsibility for the process. But if you will open them, we'll see that there are some standard components like motherboard, processor, memory blocks, nothing new for us. But of course, they have very high reliability, very good quality, and they're very well tested. And they are using the real-time operating system. So we know that if we will define an algorithm that should be repeated every second in a loop, we know it will be executed every second. So this is a real-time system. This algorithm process has the highest priority. There will be no such things like, automatic update of the system, right? Or an antivirus will start and our algorithms will slow down. No. It's a real-time system. So now let's discuss the system highway, the network. Every time we are starting a new project in the plant or in the factory, we have to discuss with the IT guy the architecture of the network. We need to do this because we will have to plug our computer to this network, our computer that performs the AI algorithm. So we need to understand where to plug it. There are different architectures. We can have one level network where the controllers and engineering stations and operator stations are connected to one network. We can have a division between the control network and the operator network. So all the controllers can be plugged into the one network, and there is another network where the engineering stations and operators stations and archiving stations are connected, and of course routers between them. We have to remember that this is a very robust system, so usually there is one way of information flow. So even if there will be a failure of a particular part of the network, there is another option for the information flow. Usually there are two redundant networks, two redundant routers. So we are sure that the failure of one network or part of the network will not stop the whole plant. Of course, in such a network, we are using the standard components like routers, switches. Of course, they are very robust. They have a good standard. They are well tested. But those are the standard components. Okay, now let's discuss the operator station. So, like I told you before, those are computers that helps to visualize the system, the industrial process. Usually, the operator have at least two screens. On one screen, he can see the process part of the process with current values of sensors, and on the other screen he observes the list of alarms. So he knows where is the threat, what are the problems he should address. And of course, he has the ability to control the process. So usually he can switch between automatic and manual mode of a particular device. In an automatic mode, he can add his bias. So let's say if we are controlling the flow, and we think as the operator that the flow is too low, we can increase the set point for the flow. So let's say the set point of the flow is calculated based on the process load, industrial process load, for instance. But we see that we are not happy with this flow. We think it should be higher. We can add the bias to the set point. We can ask for 2, 3, or 5% more for 5% higher flow, right? While still operating in the automatic mode. On the other hand, we can switch to manual mode and put the information about the desired pump load. So we are not happy with the flow, totally not happy. so we have to take care of the valve. Or I know our friend called us that he hears some strange noises from the fan, and it's better to take this fan into manual mode, reduce the load, because there is a risk of a failure. Those are normal PCs, strong but normal PCs, usually with some normal operating system. Okay, maybe I will show you some examples, right? So we can have such visualizations. We can even have such visualizations. This is very old one, but still informative, right? We can see what are the temperatures in a drum, some trends, etc., etc. We can also present some more sophisticated things in such graphics. We can present characteristics, where we are, where is the process point, on top of the characteristic, what are the stresses, for instance, calculated but by some external methods, some bar plots. So this is possible to create in such control system. And of course, please remember that the operator will not switch to another system, the web application, to observe, to get our recommendations, right? He is using the DCS only. He don't want to mix different windows from different systems. So if we want to present the operator, the dispatcher, our decisions, we have to create such operator graphics by ourselves, or we can ask the automation guy to help us. And here is the example how the operator can change the load of the device. Here we have 4 call feeders, 4 call mills, and let's say we would like to change the. Of course, the system is not connected to the plant, so everywhere we can see the 0. But let's pretend it is connected. So if we click on the device, the sub window will appear. This sub window is connected, is related with this particular device, and we can switch the mode of this device from automatic mode to manual, and from manual to automatic. Here we are not connected to the plant, so only manual mode is possible, but we can increase, for instance, the load of this device by clicking the arrows or putting the particular value in this control station. And we can see, we can then press double click or right click the mouse on the value which we would like to observe on the trend, and we can see the trend in this particular case of the feeder speed that is changing. Well, so this is the way how the operator interacts with the process. The alarming is very important. If our AI algorithm predicts the risk of a failure, it is good to raise the alarm. So we need to understand how the alarming is working. So for each variable, for each process point, for each tag, we can associate the alarm. We can define some levels. Like, for example, this is the temperature. And if the temperature is higher than a particular level, if it's the, steam temperature in the 200 megawatt unit with a drum, it probably this level would be 540, I don't know, 3 centigrades. If the temperature will exceed this level of 543 centigrades, we will raise the yellow alarm, the warning, right, to the operator. If it's higher than, I don't know, 550 centigrades, there will be a red alarm. So you should definitely do something with this, dear operator, because this is a serious threat to the process. And when the temperature will drop, the colors of the alarm will reverse. So on the end of the day, if the operator was able to handle this threat, it will go back to the green, color. Those alarms can be associated with devices, process value, even IT system. If there will be a failure of a controller, the new alarm will be raised. Okay. Yeah. So this is let's say the sensor value. If it hits the first level, first threshold, we will raise the alarm, the warning. Yeah, this signal has too low value. Then maybe that the operator will do something with this. The value will increase, but it will start to hit the higher thresholds. He will send the warning, here the serious warning, here the, let's say, the red color. So this is a serious threat. And by looking on those colors, so the operator has a list full of yellow, orange, violet, and red colors. The operator, of course, will start picking the red alarms and do something with this. In case of binary points, 2-state points, we can also set some alarms. If, for instance, we can set the alarm if the value of the point is 0, false, negative, right? So if the valve is closed, normally it should be opened, but if it's closed, we will send the alarm. The same in opposite way. We can also set the alarm if something changes its state, right? Okay. Here is such an alarm list. I had to anonymize it, so you don't see the description, name and the description. But for instance, here is some temperature, right? So the operator received the alarm that the temperature was too high. It was 870 Fahrenheit, which is too high. And yeah, please do something with this. And here you can see some green alarms. It means that there was an alarm, but now it's okay. Now it's okay. And now the most interesting component, the engineering station. From the engineering station, we can manage software and hardware. We can add new process points, define alarms, create new control sheets, new control algorithms. We can create new operator graphics. We can supervise and tune our control algorithms. So we can create new algorithms using some dedicated tools that uses AutoCAD or using tools that uses AutoCAD or tools, dedicated tools like this one. Right? So this is the definition of a loop that is executed every second. and here are the inputs, like steam flow, right? What is there? Some temperatures, etc., and some outputs. Some of them are sent directly to the actuators, to the devices. Other are sent to other control sheets. So this particular output can be an input in the other control sheet, other such an algorithm. What kind of algorithms do we have here? There are some logical algorithms like AND, OR algorithms, manual auto stations, some. There is some characteristic implemented, the PID controller that controls particular part of the process. It looks maybe complicated, but if you know how to read it, it's like, a story that is very interesting to read. And now I would like to tell you how to read it on the example. So let's start from the example where we have to control the airflow to the combustion chamber, right, in the power plant. So let's pretend that our AI algorithm tries to find the proper airflow in order to minimize CO emission, NOx emissions, and to improve the efficiency. So it reads the sensor values and it tries to find the proper airflow, the proper amount of air that is passed to the combustion chamber. So in order to do so, we need to understand how the air is passed to the combustion chamber. So first of all, we have the first control sheet where we see that there is a controller. This is the oxygen controller. So it compares the measured oxygen in the combustion chamber with the demand level of oxygen, and if there is not enough oxygen, it increases the control signal. If there is too much oxygen, it decreases the control signal. Here we have the manual auto station, so if the operator is not happy with the operation of this part of the control system, he can switch to manual mode and manually decide about the value of the control signal. We will see later what is this control signal, but now I'll just refer to it as a control signal. Here you can see that this oxygen demand is calculated based on the steam flow, so based on the parameter that represents the unit load. The higher the unit load, we need less oxygen. The lower the unit load, we need slightly more oxygen. So this characteristic that is implemented here tells us about this. Why do we want to measure oxygen in the combustion process? From theory, if we would like to maximize the efficiency of such a process, we should use the whole oxygen, right? We need this oxygen for a combustion process. But the mixing of coal particles and air is not perfect. It's not ideal. So it's good to have some safety margin of oxygen, like for example 2 or 3% of oxygen measured in a stack that is not used in the combustion process, right? Just for safety reason, because if we will have it, if you will have like 0.5% of oxygen measured in the stack, it means that there might be some gaps without oxygen in the combustion chamber, and it means we will produce a lot of CO, and we would like to avoid this. On the other hand, we can have, let's say, 10% of oxygen in the stack, but this is a pure loss, and we also would like to minimize losses. So we need to find a good compromise, a good value of this oxygen level that is as low as possible without generating too high CO emission. And of course, it's also have an effect on NOx emission, because the higher the oxygen, the better the higher the temperatures usually, and the higher NOx emissions. So we think we need to find a compromise between different factors. That is why we need the AI algorithm. So the control system tells us that, when there is a high unit load, we can have 2% of oxygen. When there is a low unit load, we can have, let's say, 3% of oxygen measured on the stack. If the operator is not happy with this, because he sees that, well, we have a high unit load, the oxygen, the set point for oxygen is 2%, but I see that the CO emission is too high. So the operator can open the window, like we did with the coal feeder. He can open the window and add a bias at, let's say, 0.5% of oxygen more. So the demand is not 2%, but it's 2.5% in order to avoid CO emission. And here is our hook. So here we can pass our optimal decision about the oxygen demand. It's not perfect. I will discuss it more in the last video, because I see there is no limiter of this value, but still we can pass this information to the control system, what should be the oxygen demand. There is the if-else statement, let's say, and the flag that controls this if-and statement. If this flag is true, then our algorithm will pass the demand for oxygen. If it's false, maybe the operator click the off button on the operator graphic, so then this flag will be false, and the control system will decide about the oxygen demand. Yeah, but this is, this will be covered in the whole new video, because it is very important to do it in a proper way. There are different ways of how to pass this information. We can, for instance, bypass the operator bias instead of sending the whole oxygen demand. But I will discuss those things later. All right, so now the PID controller try to find such a value of the control signal, so the measured oxygen equals the demand. And once again, the idea behind the PID controller also will be discussed in the next video. Then this information is passed to another control sheet, another part of the whole control strategy. And it turns out that this is a so-called O2 trim. So this is a multiplier with a value between 0.8 and 1.2 that is used here. So if we want to have more oxygen, the PID controller will calculate the control signal that will have a value higher than 1, and it means it will increase the value of this signal. And what is this signal? This is the airflow demand calculated based on the boiler master and fuel flow. So if based on the load of the boiler, right? The higher load, the higher the more steam we are producing, the higher the load of the boiler, the more air we have to pass to the combustion chamber, right? This is obvious. But if we see that we have not enough oxygen, we will even multiply this value here. If we see that there is a lot of oxygen, we can decrease this value using this multiplier, and then the oxygen controller will calculate the value of the control signal that is lower than 1. So here we have the final airflow demand, the final value of the airflow demand. But this is just a demand. We have to use some devices to pass this air to the combustion chamber. So there is another controller that compares this final airflow demand with the measured airflow. And if this measured airflow is lower than the final airflow demand, it asks the forced draft fans on the left and on the right side to increase the load. If there is too high airflow, the PID controller will decrease the control signal and the load of the forced draft fans on both sides will decrease. So if we want to, we have to decide, should we, as a developers of this AI method, we have to decide, should we want to affect the oxygen set point, or should we send decisions directly to forced draft fans? This is our decision, and we should really think about this while creating the AI algorithm that optimizes this airflow. But first we need to understand the operation of the whole system. There's also a balancer, so if the operator switched the forced draft fan on the left side to manual mode, the balancer will try to compensate the operator decisions using forced draft fan on the right side. So it's also have to be considered by our AI algorithm. So this is very, very important to understand this control system. Okay, so we was analyzing some control sheets, and they are nothing else like a special form of a computer program that executes an algorithm in a cyclic way, in a loop. Usually those control sheets are transformed into some kind of code, like say the C code, and they are compiled. Such a compiled program can be executed in a loop. First it can be loaded to the controller memory and then executed. We can tune those algorithms in online mode, so we can, change the gains, maybe change some limits, change the PID controller gain or integral time or other important parameters for this algorithm without stopping the plant. We can also load the new algorithm. We could add some new algorithms and load them into the controller memory without stopping the plant. In case of errors during the loading process, the controller automatically switches control functions to the redundant controller, to its twin. Right? But if case of mistakes in the control sheet merits, let's say we put AND instead of OR in our logical algorithm, or we will choose too high gain for our controller, we can create a control sheet with the proper syntax. But in such case, the loading process will be successful, but we can cause emergency unit shutdown or even worse. So we have to be very careful. We need to be very careful, especially when we are doing some modification when the plant is operating. So every time we should backup existing control sheets before the modification. We should inform the engineer who is responsible for the control system about changes that we want to do before loading them into the controller memory. We have to inform the process operating about changes in the control sheet, because before we load them in the controller memory, because the operator is responsible for the process, right? We should validate implemented changes in the testing environment if we have such, or in the simulator, right? Or in the virtual machine with the backup of an existing control system. Or we should at least ask the automation guy to help us validate those algorithms. And like I said, the operator is responsible for the process, so we should discuss with the operator how to minimize the threat related with the loading new algorithms into the controller memory. For example, if we are in the plant and we would like to modify this control system that we have discussed, the control system that is responsible for keeping the proper amount of oxygen, we can, the operator can take the force draft fan to manual mode, right? So even if we do some stupid things, the force draft fans will operate in the manual mode, and we will be able to look into the memory of the controller and see that all those values are strange, right? The operator can also pay special attention for some process points, right? So if we would like to change the control system that controls the temperatures of water or steam, the operator can open the operator graphics with water system or steam system and observe the temperatures of a steam. Sometimes the operator can say that right now it is not possible to modify the control algorithms because we will operate with a high load and it's unsafe to do such modifications right now. Maybe we should wait for a night shift to perform those modifications. So we should always cooperate with operators, with dispatchers. On the end of the day, they must trust us. They must trust our AI algorithms if we would like to have a successful implementation. So it's always good to discuss things with the operator. All right. And here you can see how you can modify operator graphics. For instance, you can use some dedicated elements like bars, trends, some shapes. You can drag and drop some elements that presents numbers, trends. You can add some logic to this. So, for example, if you would like to present the value of the steam temperature, you can drag and drop the element and put it on your graphic. But you can also add some logic that if the steam temperature is too high, the color of this value will switch from the black to the red. So some logic is implementation of some logic is possible here. The same here. All right, and I will discuss how to create the operator graphic dedicated for our AI algorithm in the last video. And the last element is historical data server, very important element from our point of view. and because here you can find historical data values that can be used to train the AI algorithm. You have to know that not all process points are stored in the history. So it may you may have such a situation that you will find some process values interesting to you, some process values in the operator graphic, but not all the values will be stored in the historical data server. So usually it's good to discuss what is stored in the historical data server, and if you see that something is missing, you can ask your customer, your business partner, to add this information, to add this parameter to historical data server as soon as possible. The sooner the better. If you are doing some identification experiments, because if you are changing some set point for the temperature, and you are observing how the temperature is reaching its set point, or you are changing the load of the unit, and you are changing how the flows and temperatures are changing as a response to the unit load change. You need to be in such cases you need to be sure that all the parameters that you will use to create your predictive models are defined in the historical data server. Usually such experiments are planned. There are some formal papers need to be filled in order to perform such an experiment. You have to prepare the whole unit, the whole process, to discuss things with operators. So finally, when you do the experiment, you don't want to wake up in a world where you will lost your data because not all the parameters was defined in the historical data server. So please always double check this. One more important issue. There are many ways of storing the historical values. One of the popular way is the asynchronous mode with the utilization of deadbands. So we are storing the information about the process value only if the difference between the current value and the last stored value is higher than the deadband. So if we are fluctuating around the last value, we are not storing this information. Only if there will be some essential change higher than the deadband, we will store this information. And of course, the higher the deadband is, the worse resolution of our data. We have the worst resolution of our data, because if the deadband is very narrow, we will store most of the changes. However, it's not efficient from the utilization of the memory. Right? If it will be too wide, we might lose some information crucial for our algorithm. So we should also double think how to choose the deadband. What should be the deadband? Okay, and I think we have discussed all the important components of the DCS system from the AI algorithm point of view, let's say. In the next video, I will show you some theory related with the control system, so you better understand those things, those control loops. And then in the next video, we will discuss in details how we can integrate the AI methods with the control system. Thank you. Have a good day.